Good afternoon, everyone. So, this is the last live session. This is a recap session as already pre-advertised last time. So, what we'll do, we'll just wait for a couple of more minutes. I think after 3 4 minutes, we can start. Some students actually joined in late. So, we'll just wait for 3 4 minutes and then I guess we can start with our live session. So, one of the students had asked a question. I have one clarification. You take up this matter with the NPTEL team. We don't have access to those details. Our job is only to show the live session. So you can take up this matter with them. You write them an email and tell tell them about your problem. Hopefully they will solve it. They have a record of everything, and I guess it will be solved. No worries. Is anyone among you appearing for exams of this course? So no one. It doesn't matter. So I think we should start. It's already 3 4. We can start. So let me just introduce myself, probably for the last time in this course. So my name is Musa Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. We are here at live session number 13, basically a live problem solving session for the course Digital Circuit that is being taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. So far we have done 12 live problem solving sessions pertaining to the 12-week course. So every week we used to meet from 3 p.m. to 5 p.m. to discuss the problems pertaining to that week's contents. This is the last session, it's mostly a recap session. So what I have done here is I have some 15 to 16 problems. I have picked some 15 to 16 problems. Few of them I have already discussed in my previous live sessions, and some of them are new, some of them are new for you guys. So it will just give you a brief recap of the things that we have done so far. So I kept some problems that I've found were important, I have taken up them again, and some of them are new, so that should recollect your concepts and all. Other than that, since the role is pretty small, live audience, so what you can do is, if at any time you have some doubts, you can ask in by unmuting yourself. But if you feel comfortable in the chat box, you can always use the chat box as well. I'll give you ample time to ask in your doubts after a problem is solved, and you can always ask in your doubts at that time. So this was your content of the course, containing 12 weeks material, starting from the number system, followed by the Boolean algebra, logic minimization, combination logic, logic gates, arithmetic circuits, then sequential circuits, counter shifters, followed by data converters. Ultimately, we had a brief overview of the semiconductor memories, and we concluded with the microprocessor, which was spanning over 2 weeks, right? So I have total 15 to 16 problems. Some of the problems I'll show the solution first, and then for some problems I'll ask you guys to solve first, and then I'll show the solution. So that is our usual modus operandi. We'll go along those lines only. So let's just start with the first question of today's live session. I think it should be from the logic minimization part of the course. So the question asks us, the output Y in the circuit below is always when option A, two or more inputs of P, Q, R are 0. Option B, two or more inputs, just a second, two or more inputs are 1. Any odd number of inputs is 0. Any odd number of inputs is 1. So we need to find out which of the conditions fulfills the required circuit. So let's just label our output. So first label the gates. So we'll call this as gate 1, gate 2, gate 3, gate 4, gate 5, and ultimately gate 6. And let's just term these outputs as x1, x2. Similarly, this here as x3, this here as x4, this here as x5, and this is y it is. So no need to label this one. So what we have here is, we have first the x1, right? X1 is basically this input and this input, so it's PQ, so it goes to the inputs of NAND gate, so it's PQ bar, that is basically PQ complement. Then we have X2, which is Q and R, QR bar. Then X3 has inputs R and this thing, this is P, so I'll just write PR complement. Then for the NAND gate 4, x1 and x2 are its inputs. So x4 I can write simply as x1 x2 whole complement, right? So x4 will be equal to pq bar dot qr bar, then whole bar. Now I'll use a law. I think by now we'll almost be knowing which law I am going to use to evaluate this part. I'm taking help of which law to evaluate this part. Anyone in the chat box can write the answer. Yeah, thank you. So De Morgan's law. So it will be PQ bar bar plus QR complement whole complement. So it will be PQ plus QR. By plus I mean it's a OR operation. By now you must be familiar with that. Now we have X5. So X5 is having same inputs. Can you anyone tell me what is the functionality of this gate? Just a second, give me a second. What is the functionality of this gate? What will be out? What will be the output here? What is the output? I'll just redraw it. I guess the question is not clear. I want you guys to tell me. I have this NAND gate and I have this input A. What is the output? Complement. Yeah, that means it's act as a NOT gate. So this X5 is simply your X4 complement, and that is PQ plus QR whole complement, right? Now what I'm left here is I can use De Morgan's law here as well. So it is PQ bar dot QR bar. Now output of NAND gate 6, that is Y, is equal to X5 here and X3 here whole complement. Your X5 is PQ complement dot QR complement, and then you have your X3, that is somewhere here, yeah, PR complement, and then you have this whole complement. Again using De Morgan's law, so just PQ. So again using De Morgan's law, so it's PQ complement whole complement plus QR complement whole complement plus PR complement whole complement, and when you evaluate it, simply PQ plus QR plus PR. So my output is simply this of this logic circuit. So Y equal to 1 when any one of these three terms is 1. So when any one of these three terms is 1 is basically when any of the two inputs are 1. So either PQ is 1 or QR is 1 or PR is 1. So any one of these combinations is 1. That means 2 out of the 3 inputs are 1. So option B. So option B is the required answer. So how did you deduce it's A? I guess it's clear. I hope it's clear. Oh, it's fine. So any doubts in the audience? Anyone? Anyone having some doubts? So if not, then we can have we can proceed to question number two. So I have marked this question. So what I what I would like is you guys to solve it first and write your answer, only the correct option. No need to write the complete answer, only the correct option in the chat box. I'll give you a couple of minutes. Three minutes should be fine for this question, and then I'll show the solution. So let me just read the question for you guys. It states that design a 4-bit odd parity generator using a 4:1 multiplexer considering ABS select lines. I'll repeat it once again. Design a 4-bit odd parity generator using 4:1 multiplexer considering ABS select line. So you have these four options and you need to tell which one is the correct option. Do it. I'll just give you some few minutes and then I can show you the solution. Has anyone done it? Just use few more seconds and then I can show you the solution. So now let me just show you the solution. So the question asks us to design a 4-bit odd parity generator. So let's have a 4-bit truth table first. A, then we have B, C, and D. Yeah. So one of the students is done. So let's just check the truth table first. Yeah. 0, 1, 0. Somewhere I have made a mistake. Let me just draw it again. Okay, it's fine. Yeah. So only one of the students has, I guess, done it so far. Yeah. So can anyone tell me this is the F your function parity bit generator? What will be F here equal to in the first case? Here, I mean to say F is equal to, we are checking for odd bit parity generator. So what will be F equal to? Yeah, it will be 1. Here it will be, here 0. Here also it will be 0. Here it will be 1. Again 0 here. Here it will be 1 because we want total number of ones to be odd. So we'll add 1 here. Then again 1 here. Then 0 here. Then 0 here. Then 1 here. Then 1 here. Then 0 here. Then 1 here. 0, 0, and then 1. 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1. Correct. Now we'll just make a K map for a 4-bit, and we'll have AB here, CD here, and these are our select lines as well. 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Now we'll mark all the ones. So here, 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 and here. You can check the truth table to verify these. So when AB is equal to 0, 0, which input line will be selected? When AB is equal to 0, 0 for a 4:1 mux, which input line will be selected? Anyone? Thank you. So it will be I0. So when 0, 0, I0 is selected, so I0 is simply your this thing and this thing. So this is C bar D bar plus CD. This is nothing but your XNOR gate of between C and D. Then for this I1 will be selected, and I1 will be equal to this thing and this thing. So C bar D plus CD bar, that is C XOR D. Which input line is this? This is I2. This is 1, 1. Be careful here. Huh? So this is I1. This is I3. Sorry, this is I3. So I3 will be equal to again this thing C XOR D, and this is your I2. So it is equal to C XOR D. So your I0 equal to your I0 equal to I2. Yeah, your I0 equal to I3. Your I0 equal to I3. C is equal to C XOR D. Your I1 equal to I2 equal to C XOR D. So option A, as rightly pointed out by one of the students, is the correct answer. Now I have this question, which states that consider the equation 1, 2, 3 to the base 5 in the base 5 system and x8 in base y system with x and y as unknowns. The number of possible solutions is, so we have this equation with us, 1, 2, 3 to the base 5 and x8 to the base y, and we need to find out the number of possible solutions. So let's just expand them. So this will be equal to 3 into 5 raised to power 0 plus 2 into 5 raised to power 1 plus 1 into 5 raised to power 2 equals to x into y raised to power 1, that is y only, and 8 into y raised to power 0. So this is 25 plus 10 plus 3 equal to xy plus 8. That implies xy is equal to 38 minus 8. That implies xy is equal to 30. So your x can be equal to 1 and y can be equal to 30. Your x can be equal to 2 and your y can be equal to 15. Your x can be equal to 3 and your y can be equal to 10. X equal to 4. I'm only taking integers because it's a base, so it is only positive integers. So it can't be 4, so we don't have any combination with x equal to 4. Then your x equal to 5, y is equal to 6. So is this the solution? Can anyone confirm whether x equal to 5, y equal to 6 can be a solution to this equation? Because we need to check whether these combinations are true or not. So is x equal to 5 and y equal to 6 a solution? So someone is written yes. Are you sure? Can you please check it once again? Yes, it's not a solution. What is the reason? Anyone? What is the reason why this condition doesn't hold? Why this thing doesn't hold? Anyone? Correct. That's the reason, because y has to be less than 8. No, no. Y has to be greater than 8. Y has to be greater than 8. I guess it was a typo. Y has to be greater than 8. Because 8 exists in this system, so that means y is greater than 8. It can be 9, 10, and so on. So I guess you meant y greater than 8. So, so how many solutions then there exist? There only exist three possible solutions. So option A is the correct answer. Any doubts in here? So let's proceed to question number 4 of today's live session. It says that the logic functionality realized by the circuit shown below is. So the question asks us, what is the logic functionality realized by the circuit? Before we proceed, can anyone tell me what is this? The highlighted one that I have highlighted. So anyone, what is this? Anyone else? So they are MOSFETs and they are well, PMOS or NMOS? Are they PMOS or NMOS? Okay, just tell me what is this? Does anyone here identify this circuit? What is this? Yeah, complementary. But it has a CMOS means PMOS and NMOS. That's fine. But it has a particular name, CMOS dash, or it is a particular circuit. It has a particular functionality. What is that functionality, or what is the name of the circuit? So let me put in this way. What does this circuit do? What is its operation? This one. I'm talking about this one. It is a CMOS dash. We call it CMOS inverter, right? This is CMOS inverter, or your NOT gate in short. By the way, what does C stand for in CMOS? Thank you. It stands for complementary. So going along these lines, what is this? Is it a PMOS or an NMOS? Thank you. And this is PMOS. So you are able to identify NMOS and PMOS. Similarly, what is this? Thank you. This is NMOS and this is also NMOS. Both of them are NMOS. So from this symbol, how did you differentiate them? By having this bubble here, right? You now this was not needed, but this was in fact needed, I should say. Yeah. Now the question, I'm a bit digressing, so bear with me for a couple of minutes. So this is your PMOS, this is your NMOS, so this is A, B, C. So can you tell me which among A, B, C is source, gate, and drain? So one of the students has written B is gate. That's correct. What about source and drain? So let's go step by step. What is A? So some say source. That means C is drain. This is wrong. So that means C is source and A is drain, right? This is also wrong. Whether a MOSFET terminal is source or drain, it depends on the polarity, not on the terminal itself. Always remember, keep this thing in mind. I won't dive into details, but just for the sake of it, keep this thing in mind. I can even say mug it up. MOSFET is a symmetric device, right? So when you have an N MOSFET, its polarity, that is the potential, determines whether the particular terminal is a source or a drain. If this for a N MOSFET, keep in mind, if for an N MOSFET, if it is at a higher potential, this thing becomes drain as compared to C. So if A is at a higher potential than C, so A is your drain, C is your source. In PMOS, what we have here is PMOS, its source is at higher potential and drain is at a lower potential. In PMOS, it's the reverse. But mostly, just remember for NMOSFET, just remember if A is at higher potential, that means if one of the terminal is at higher potential than the other, so the one terminal which is at the higher potential is the drain, and the one which is at the lower potential is the source. And this is simply gate, which you almost all of you identified. So this was just the outline I wanted to give you. Mostly in this course, you don't teach these things, but I wanted to give you a brief idea about this. So now let's go back to the question. So we need to find out the logic functionality realized by the circuit shown below. So what we have here is NMOS and we have gate. So when gate voltage is greater than some threshold voltage, so let's not go there. So when gate voltage, we'll just talk about in digital language itself. When gate is equal to 1, it's on, and when gate is equal to 0, it's off. So let's create a truth table A, B, and let's have Y here. So A 0 0 0 1 1 0 1 1. So when A is 0 and B is 0, that means this gate is off. That means this N MOSFET is off. And B bar is 1. That means this gate is on. That means this Y is connected to the ground. That means by ground I mean 0. Then my next case is A equal to 0, so A is 0, B equal to 1, so this is on, and B bar is equal to 0, so this is off. Again, this is tied up to ground, so this is 0. Then A is 1, A is 1, and B is 0. B is 0, that means this is off, this is on, so connected to ground, so this is 0. Final case is A equal to 1, so A is equal to 1, B is equal to 1, that means this is on, this is off, so this is connected to here, so Y is equal to 1, and this is your which gate? AND gate. Thank you very much. So option D is the correct answer. Now question 5. I would like you guys to solve first. I'll just give you a couple of minutes. It should not take more than that. So it asks us the reduced circuit of the following original circuit is. So this is the original circuit that is given to you. You need to draw its reduced circuit. So do it. Just tell me the correct answer. Anyone? So let me just show you the solution, or if you guys are doing, do it side by side. So no worries, you can always follow up. So let's just mark these points as this is x1, this is x2, this is your f. So your f is basically equal to x1 dot x2, right? And x1 is equal to a plus b bar plus c bar, and your x2 equal to what is this, a plus b bar plus c. That means f is equal to a plus b bar plus c bar dot a plus b bar plus c whole bar. No, not whole bar, not whole bar. Yeah. So then f is equal to a dot a is a plus ab bar plus ac plus ab bar plus b bar plus b bar c plus ac bar plus c bar b bar plus c bar, or cc bar. Yeah, cc bar. So f is equal to then a plus ab bar plus ac plus ab bar plus b bar plus b bar c plus ac bar, and c dot c bar is 0. So this is 0. Then I'll rearrange the terms. So a plus ab bar plus ac plus ab bar plus ac bar plus b bar plus b bar c plus b bar c bar. There should be 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, b bar c. Now you will take a common. So we have 1 plus b bar plus c plus b bar plus c bar. Then you take b bar common. So it's 1 plus c plus c bar. So can anyone tell me what is this thing equal to? The whole thing in the bracket? Yes, this is a and this is b bar, because you know this thing, 1 plus anything is equal to 1. So this thing is equal to 1, then times a is a, then b bar. So your f is simply a b complement and going to two input, so no, OR gate. So option D is the correct answer. Now I have this question which states that determine the inputs of the 4:1 multiplexer to make the output Q equal to xy plus z, where x is MSB and z is LSB. Use x and y as select lines and z as input variable. So your MSBs are your select lines and your LSB is your input variable. So we have Q equal to xy plus z, that implies Q is equal to xy z plus z bar. Basically I want to write it in SOP form, that's why I'm doing this. Then x plus x bar z, so Q is equal to xy z plus xy z bar plus xz plus x bar z. Q is equal to xy z plus xy z bar plus x z y plus y bar x bar z y plus y bar. So it is equal to xyz plus xyz bar plus xyz plus xy bar z plus x bar yz plus x bar y bar z. Q is equal to summation of product 1, 3, 5, 6, 7. You can check this one. Q is equal to products, summation of products 1, 3, 5, 6, 7. Now I'll have the implementation table here for 4 is to 1 marks. I'll write D0, D1, that is basically input lines, D2 and D3, and here I'll write Z bar, here I'll write Z bar, here I'll write Z. Just give me a second, just give me a second. So this is Z bar and this is Z. Here I'll write 0. So what should I write here? So what should I write here? Anyone? Here I have written 0. What should I write here? So here I'll write 1, here I write 2, 3, 4, 5, 6, 7. Because your Z is your LSB. If it was MSB, I would have written 1 here. Here I would have written 1, then 2, then 3, then 4, 5, 6, 7. In your lecture notes, you can refer to these types of questions, and even in my live session, I think week 5, you can refer to those live session as well. Now I will encircle all those minterms that are 1. So it's 1, 3, 5, 6, 7. So that implies, so D0 is equal to Z, D1 is equal to Z, D2 is equal to Z, D3 is equal to 1. So D0, D1, D2 are Z and D3 is equal to 1. So option A, yeah, option A is your correct answer. Now I have this question number 7. I think you can expect to get the canonical SOP humanized right. So why did we not multiply Z with we multiplied. See, first we multiplied it with X and X bar, then we multiplied both of those terms with Y and Y bar. You can check. Got it? Yeah. No issues, no issues. You can ask question anytime. Yeah, so we have this question: convert T flip flop to D flip flop. So this is basically a generic kind of a conversion problem. By now, you guys will be knowing the answer to this as well. So why I kept it here is because I feel like it's my own experience that these types of problems in one way or the other will find its way in the exams. So conversion problems of flip flops, I think even if it doesn't, it's something that you should be experienced with. So you have basically these 5 points you need to remember while doing these conversion problems. So number one point is that you have to identify which is the required flip flop, which is the available flip flop. Then you have to make a characteristic table of the required flip flop, followed by making an excitation table of available flip flop, then writing the characteristic equation, and ultimately, I should say, writing the Boolean expression of available flip flop, and ultimately you'll draw the circuit. So we have a problem of conversion of T flip-flop to D flip-flop. So my available flip-flop is my T and my required is my D, right? Now I'll make a characteristic table of required flip-flops. So I will have Qn and D. So I'll have 0, 0, 0, 1, 1, 0, 1, 1. And here I'll have Qn plus 1. So for D flip-flop, we know Qn plus 1 is simply D. So it's 0, 1, 0, 1. Now here I'll make the excitation table of T flip-flop. I'll just take Qn and Qn plus 1. I know that it's an XOR operation. So it's 0, 0, 1 it's 1, 1, 0 it's 1, and 1, 1 it's 0. Now I will write down the equation for T flip-flop in terms of Qn and D, and I can easily see that T is Qn XOR with D. That means if I have a T flip-flop, I take its output and I have this input which is D. I do an XOR operation. This whole thing is a D flip-flop. Got it? I think you people are familiar with these types of questions, but I wanted this to be here. Now I have a question which states that simplify Boolean expressions for the customized priority encoder given in the table below. So we need to simplify the expressions for the priority encoder given below. My outputs are y1, y0 and v. So let's just first take the output v and create a Karnaugh map for it. So since there are four variables including the enable one, I'll have from here I'll have enable comma d2, this is v, and here I have d1 d0. This is 0 0 0 1 1 1 1 0. So for enable, when enable is 0, I have don't care on all of them. So v is 1 only when enable and d2 is 1. So this row 1 1 row is 1, and it's also 1 when I have 101 combination, 101 combination, and there is a don't care on d0. So 101 combination is this one and this one, and it's also 1 when I have combination of 1 0 0 0 1. So this is this one. Now minimizing it, I can create a square like this, a square like this, and a square like this. So v is simply equal to enable d2 plus enable d0 plus enable d1. So v is equal to enable d2 plus d1 plus d0. Now let's check for y is 0. So here I have enable d2, here I have d1 d0. So it's 0 0 0 1 1 1 1 0 1 1 1 1 0. So y0 is 1 for 1 0 1 and don't care 1 0 1 1 0 1. So this is basically, let me just erase it, this case. I'm checking this case, so it's 1 0 1, and that is this one and this one, as d0 is don't care, and it's also 1 for 1 0 0 0 1 for this one, right? So I can create this and I can create this. So my output y0 is equal to enable d2 bar d0 plus enable d2 bar d1. So you can write enable d2 bar d0 plus d1. Now I have to check for in output y1. So output y1 is 1 for 1 1 case. So this thing, and it's also 1 for 1001, this thing. So I'll have this and I'll have this. So y1 is enable d2 plus enable d1 bar d0. So y1 is enable d2 plus d1 bar d0. So these were your simplified expressions for your outputs. Now I have question number 9 of today's live session. It says that initial contents of the following flip-flops are ABCE equal to 0110. What are the contents of ABCE after 2 clock cycles? So we have A, B, C, E. So we have clock here. We have the initial state here for which it is 0110. So anyone can tell me what type of counter is this? Can anyone tell me which type of counter is this? Yes, thank you. This is a twisted ring counter or Johnson counter, where your output complement is connected here. So 0110, since E is 0, E bar is 1. In next clock cycle, this A will be 1, then this 011 will propagate 011. In next clock cycle, it will be 0 and 101 will propagate 101. So after second clock pulse, my output is 0101, A, B, C, E. That is option B, which is the correct answer. So now I have a question for you guys to solve, which says that consider the equation 5p364 in the base 8 system equal to 5afq in the base 16 system. The value of p and q are, so you have this equation with you, so you need to find out the value of p and q. So do it. I'll just give you 2-3 minutes. You should be able to solve it within that time. So you have this question with you, which says that 5p364 to the base 8 equal to 5afq to the base 16. The value of p and q are dash. So you need to find out the value of p and q. Do it, and then I can show you the solution afterwards. So has anyone done it or about to? So let me just show you the solution. We'll just expand the left hand side and right hand side. So we can write it like this. We can write it like this: 8 raised to power 0 multiplied by 4 plus 8 raised to power 1 multiplied by 6 plus 8 raised to power 2 multiplied by 3 plus 8 raised to power 3 multiplied by p plus 8 raised to power 4 multiplied by 5 equal to 5 into 16 raised to power 3, 5 into 15 into 16 square. 15 is coming from this, sorry, 10. It should be 10 plus 15 into 16 plus q into 16 raised to power 0. So see, now what we'll do is we'll have it like this: 5 into, you have this thing as 8 raised to power 4. This is nothing but 2 cube, because 8 is 2 cube raised to power 4. So this is 2 raised to power 12, correct? Yeah, yeah. Uh, thank you for your answer. We'll just see whether this is correct or not. So 2 raised to power 12, and this 2 raised to power 12 you can easily write 2 raised to power 4, 4 raised to power 3. So that implies it's 16 raised to power 3. So 8 raised to power 4 is equal to 16 raised to power 3. Then I'll have 8 cube, that is 2 raised to power 3, 4 raised to power 3, 2 raised to power 9, right? 2 raised to power 3 or 4. You can easily write it like this: 2 raised to power 4, 4 raised to power 2 multiplied by 2. So this is 16 raised to power 2 multiplied by 2. So you have it 2 into p into 16 raised to power 2 plus your 8 square is 2 raised to power 3 whole square is 2 raised to power 4, it's 2 raised to power 6. So it's 2 raised to power 4 multiplied by 2 raised to power 2, that is 2 raised to power 16 multiplied by 4. So it's 4 into 3 into 16 plus then you have 6 into 8, that is 48, that is simply your 3 into 16, right? Plus 4 plus 4 into 8 raised to power 0, you can write 16 raised to power 0 equal to 5 into 16 raised to power 3 plus 10 into 16 raised to power 2 plus 15 into 16 plus q into 16 raised to power 0. Why I did this thing, I'll tell you in this step. 5 into 16 raised to power 3 plus 2p into 16 raised to power 2. Combining these two, it will become 15 into 16 plus 4 into 16 raised to power 0 is equal to 5 into 16 cube plus 10 into 16 square plus 15 into 16 plus q into 16 raised to power 0. I did this because I can now easily compare the coefficients of each of these terms. So you can see this left hand side is equal to right hand side, and I have made them into same form by, and now what I will do is I'll compare the coefficients. So this 5 is equal to 5, this 15 is equal to 15, this 2p is equal to 10, and this, what should I say, this 4 is equal to q. That implies 2p is equal to 10 and implies p is equal to 5, q is equal to 4 simply. That is option A. Is it clear? So now we have question number 11. It asks us the truth table of XY flip-flop is shown below. Design the flip-flop using JK flip-flop. This is a problem of conversion again. So this is our required, this is our available. So I'll have X, Y, Q, N. So I'm making a characteristic table of required flip-flop. So it's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So for x and y equal to 0, 0, qn is qn plus 1 is equal to qn bar. So it is 1, 0 simply. I'm checking this condition. For x and y equal to 0, 1, x and y equal to 0, 1, my output is 1. For x and y equal to 1, 0, my output is 0, qn plus 1. For 1, 1, it's qn bar, so it will be 1, 0. So we are done with the third step, that is making characteristic. Second step, making characteristic table of the required flip flop. Now drawing the excitation table of the available flip flop. I know for a fact qn and qn plus 1, j and k, 0, 0, 1, 1, 0, 1, 1. This thing is equal to 0, x, 1, x, x1 and x0. This is your excitation table. You know these things now. So when qn is equal to 0 and qn plus 1 is equal to 1, so this is 0, 1, that is this thing. Jk is equal to 1 x. When it's 1, 0, it's x1. When it's 0, 1, it's 1x. When it's 1, 1, it's x0. Similarly, I can write it like 0x, x1, 1x, x1. So I have this thing. Now what I will do is I'll just write the Boolean expression for j and k. So j will be equal to, I'll have here is x, y, q, n. So it is, I'm filling this thing up, 1, don't care, 1, don't care, 1. You can always cross check these. So it's this thing and this thing. So that implies j is equal to x bar plus y. Now for k equals to, this is your x, this is your y, k. I'll fill the table. It's like this. So it's this thing and this thing. So k is equal to x plus y bar. So k is your x plus y bar, j is your x bar plus y. So that is option D. You got it? Any doubts? Now I have question number 12 with me. It states that the following synchronous sequential circuit is designed with a flip-flop, JK flip-flop and a TE flip-flop with state with J equal to A plus B bar, K equal to A bar plus B and TB equal to A. If the initial state is 0, 0, then find the sequence of states visited by the circuit. Can you guys do it? I'll just give you a couple of minutes and then I can show you the solution. Has anyone done it? Thank you. Yeah. So we have this for a JK flip-flop. My Qn plus 1 is equal to JQ bar plus K bar Q. So here I have my output as An plus 1, which will be equal to Ja bar plus K bar A, right? So it will be J, A is my A plus J, sorry, J is my A plus B bar, and K is my A bar plus B and then bar A. So it's A dot A bar is 0, so it's A bar B bar plus I can use De Morgan's law here, so it's A bar plus B whole bar, so it's A dot B bar dot A. So this thing is equal to A bar B bar plus A B bar, and this thing is equal to B bar A plus A bar. A plus A bar, you know, is equal to 1, so this thing is equal to B bar. So An plus 1 is equal to B bar. For TB, so I'll just write B is equal to, we know for T flip-flop, the output Qn plus 1 is equal to T XOR with Q. So it's TB XOR with Q, so it's T is A XOR with B. So I'll have this thing A, B, An plus 1, Bn plus 1, 0, 0, 0, 1, 1, 0, 1, 1. So when An plus 1 is simply B bar, so it's 1, 0, 1, 0, and Bn plus 1 is the XOR operation, so it's 0, 1, 1, 0 between A and B. So if my initial state is 0, 0, so this is my present state. If my initial state is 0, 0, my next state will be 1, 0. If I'm at 1, 0, I'm at 1, 0, my next state will be 1, 1. If I'm at 1, 1, my next state will be 0, 0. So it's 0, 0, 1, 0, 1, 1, 0, 0, option B, as rightly done by one of the students. Now I have question number 13, which states that suppose the Johnson counter, 8-bit Johnson counter is initialized with the sequence 00000 in the decimal representation. What is the mean value of its counting states? So we need to find out the mean value of the counting states. So my first state is 000, then my next state will be 1000000, then 110000, then 11100000, so on up to 1111111. Then it will be 0 1 1 1 1 1 1, then it will be 0 0 1 1 1 1 1, so on up to 0 0 0 0 0 0 0 1. So how many states will be there in total? Anyone? For a 8-bit Johnson counter, how many states will be there? So I'll repeat again, 8-bit Johnson counter will have how many states? How many counting states? I think you should be knowing this. N-bit Johnson counter has how many states? 2n, correct. So here it will be 16 states. So this decimal value is 0. This is 128, this is 192, this is 224, then I have 240, then I have 248, then I have 252, then I have 254, then this is 255, then I have 120, then I have 63, then I have no 127, then I have 127, then I have 127, then I have 63, then I have 31, then I have 15, then I have 7, then I have 3, and then I have 1. So 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you'll sum them up, everything divided by 16. So 0 plus 1 to 8 plus 192 plus 224 plus 240 plus 248 plus 252 plus 254 plus 255 plus 7 plus 63 plus 31 plus 15 plus 7 plus 3 plus 1 divided by 16. This thing is equal to 127.5. So option C is the correct answer. So in a R2R ladder deck, if the input is 1011, Vref equal to 20 volt, then find the output voltage. So we can do it like this. So here N is equal to 4. My input is equal to 1011. Its decimal equivalent Vin is equal to 8 plus 2 is 10, 10 plus 1 is 11. And then my output voltage will then be equal to Vref by 2 raised power n multiplied by Vin. So it is equal to Vref is how much? 20 volts divided by 2 raised power 4 multiplied by 11. So it's 20 divided by 2 raised power 4 is 16 multiplied by 11. So it's equal to 13.75. So option B is the correct answer. Then I have question number 15. How many data and data input and address input lines are required for 128K cross 16 memory? So I have address input lines as this, termed by P, and data by N. Number of locations is equal to M, and we know that 2 raised power P, that is 2 raised power number of address lines, is equal to number of memory locations equal to M. So 2 raised power P is equal to 128K. So 2 raised power P, so 128 I can write 2 raised power 7, and 1K is simply your 1024, that is 2 raised power 10. That implies 2 raised power P is equal to 2 raised power 17. That implies P is equal to 17 and N is equal to 16. So option B is the correct answer, as rightly pointed out by one of the students. Oh, I think I did it wrong. It's 16. So data is 16. I need to write data first. Yeah, I need to write data lines first. So option D is the correct answer. Give me a second. I don't know what's the issue with this PowerPoint. Keeps on hanging and hanging. So let's just redo this. 2 raised power P is equal to 2 raised power 7, 2 raised power 10. P is equal to 17 and N is equal to 16. So D is right answer, because we need to write data input lines first. Then question number 16 of today's live session is we have to find the F1 and F2. What are F1 and F2 equal to? So this is AND gate, AND gate, AND gate. So I'll just write as AND of 1 is equal to, So this is this thing and this thing. So it's A bar C bar, A bar C, A bar C. I think it's A bar C. It's A bar and one is A bar C bar. Yeah, A bar C bar. Then I have and 2 which is equal to C, B and A. What is A, B, C? This. Then I have and of 4 which is equal to and of 4 is equal to this thing C, C and A. So it's A, C. And of 3 is equal to B bar, C bar. Now OR of 1. So we'll have this thing. OR of 1. This thing is equal to this and this. So and of 3 plus and of 2. That is and 2 is ABC plus and of 3 is B bar, C bar. Is it? Oh, yeah, it's one more. And of 1 is also there. So and of 1 is A bar, C bar. Then I have OR of 2, which is this thing and this thing. So it's and of 2, that is ABC plus and of 4, that is AC. Right. Now I have F2. Be mindful of these notations. This is F1, this is F2. So F1 is equal to OR of 2 XOR with this thing, XOR with 1. So I'll just draw the truth table here, A, B and XOR 0 0 0 1 1 1 1 0 or 0 1 1 0. So when one of the input is 1, my output is B bar. So if it was 0, it is 1. If it was 1, output will be its complement. So if I fix one of the inputs to 1, then the output of XOR gate is complement of the other input. So that implies F1 is equal to OR of 2 complement. So it's A B C plus AC whole complement. So it's I can take AC common and I have 1 plus C whole bar. So it's simply AC complement because 1 plus C is 1. So AC complement, I can have A complement plus C complement using De Morgan's law. And if I have to write the sum of minterms, this is simply sum of minterms wherever there is A complement. So A is your MSB and C is your LSB. So wherever A is 0, it will be 1. So it is 0, 1, 2, 3 coming from the A complement terms, and from the C complement terms it will be 0, 2, 4, 6. 0, 2, 4, 6. So 4 and 6. Then F2 is equal to OR of 1 XOR with 0. So OR of 1 XOR with 0. So when one of the input is fixed to 0, output is simply equal to other input. So F2 is equal to OR of 1. So OR of 1 is this thing, A B C plus B bar C bar plus A bar C bar. If you check this, this is equal to summation of terms 0, 2, 4, 7. So option A is the correct answer. So that was all for this live session of, or I should say, the recap session. If you have any doubts from this session, please let me know. Otherwise, we can close the session. So I think there are, so once show question number 14. Yeah, so we have this R to R ladder deck. So you can simply write your output equal to V reference divided by 2 raised power n multiplied by V in. V in is your simply the decimal equivalent of the digital input. Digital input is 1011, and when you convert this 1011 to decimal, it becomes 11. Plugging these values, just do the maths, you get the answer. Got it? So